I'm a PhD student at Alfred Wenger Institute in Potsdam. And like already introduced, I will talk about some work that me and colleagues did on marine cold air outbreaks and surface heat fluxes in CARRA and ERA5. And the reason I'm interested in marine cold air outbreaks is really because I'm interested in ocean atmosphere heat exchanges. So as our focus region is the Svalbard and Fram Strait, and as you can see on this map here, we have quite warm sea surface temperatures due to the warm West Spitsbergen current. And therefore, in the wintertime, we have a large temperature contrast between surface and atmosphere, and therefore large fluxes, which are then further modulated by oceanic and atmospheric variables, such as the MCOs that I will focus on in this presentation. So briefly, MCOs or marine cold air outbreaks are just cold, dry air masses being advected over the ice edge, extracting a lot of heat and moisture from the ocean surface. So what we did was to calculate a marine cold air outbreak index, defined as the difference in potential skin temperature and potential temperature at 850 hectopascal for the ice-free Fram Strait. And then we used the output surface sensible and latent heat flux from CARRA and ERA5. And we've been looking at the extended winter surface for roughly the last 30 years. So on the right-hand side, we see a lot of wiggly lines. These are time series for each of the winter months, November through March, of the marine cold air outbreak indices and the surface heat fluxes. And I would just like to point out a few things. So the first is that, yes, obviously there is a strong covariability in the MCO index, that is the black lines for CARRA and the gray lines for ERA5, and the surface heat fluxes. So when the MCO index is high, the fluxes are high like we would expect. But the second thing that we can see is that there is quite a large difference in magnitude. So for instance, the sensible heat flux, abbreviated here SSHF, the dash dotted lines, is substantially higher in CARRA than in ERA5 throughout the period, while the opposite then is true for the latent heat flux, which is somewhat higher in ERA5 than in CARRA for all the months. The MCO indices are more similar in magnitude, but at least for the first 2 decades, slightly higher in ERA5. Since this just concerned the ice-free part of the Fram Strait, I would also like to show one figure from the different surface types, so to see how it differs over ice as well. So here I've plotted CARRA versus ERA5, again, the sensible heat flux and the latent, but this time for open ocean, marginal ice zone, and sea ice. So we can see again that sensible heat flux is larger in CARRA, latent larger in ERA5, but also that the differences for the sensible heat flux scales with magnitude. So we really find the largest difference over ice-free ocean because this is where the fluxes themselves are large. However, when we normalize the differences between their analysis with the magnitude of the flux over each respective surface category, we found that these normalized relative differences are actually largest over the sea ice, and they are especially large than for the latent heat flux. And since previous studies indicate that ERA5 overestimate the latent heat flux, that might be a good sign for CARRA, that it's then a little bit lower than ERA5. Okay, so we've already talked about how the temperature difference between surface and atmosphere, which is then captured by the MCO index, affects the heat fluxes, but of course, so does the wind speed. So to kind of untangle the effects of both these, we looked at wind speed at 10-meter height and MCO index versus the fluxes. So we found that the fluxes, the MCO index is more strongly correlated with both the sensible and latent heat flux than the wind speed is. However, when the MCO index have high values, then there is a strong relationship between the fluxes and the wind speed. So for instance, if we look at subplot A, that will be the wind speed versus the sensible heat flux in CARRA. We can see then that for these blue and purple dots, when we have a big surface atmosphere temperature differences of 12 degrees or so, we also have a very strong relationship between the wind speed and the sensible heat flux. And the same goes for the latent heat flux in the right column and also ERA5 in the bottom. So the question that then arises is, why are the fluxes different? And I don't have a very straightforward answer to that, but some ideas about the sensible heat flux. As we saw in the beginning, the MCO index is sometimes a little bit higher in CARRA, which would promote higher sensible heat flux. As we can see in the box plot here, the maximum wind speed is also a bit higher in CARRA, which would actually promote both fluxes. But we also found that for a given MCO strength and wind speed, we still see higher sensible heat fluxes in CARRA and ERA5. So taking a more statistical approach, it seems that the CARRA sensible heat flux responds more strongly to both predictors. And for the latent heat flux, then the opposite is true, that here our regression coefficients were higher for ERA5 than for CARRA. So the latent heat flux somehow cares more about both the wind speed and the MCO index in ERA5. In addition to that, of course, humidity differences could play a role, and we didn't assess that specifically. It's also expected to be, to some extent, correlated with the temperature difference. So before concluding, I would like to take a brief look into the vertical and see what happens to the atmospheric column during these cold air outbreaks. So here we have, again, the extended winter wind conditions for CARRA in the top left corner. And then we have, on the right-hand side, the MCO anomalies in CARRA, so MCO conditions minus mean conditions. And as we can see, and yeah, I should probably say we're looking at the cross-section along through Fram Strait from north to south along, or from south to north actually, along longitude 6, from the surface approximately up to the height of the tropopause. So we can see then that the entire troposphere is colder and has a lower specific humidity during MCOs, as expected. We can also see in the distribution of the temperature anomalies that the largest anomalies are found in the marginal ice zone or near the ice edge. So over the sea ice, it's already very cold. Even when there's not an MCO, there's not a huge difference. Whereas over the open ocean, the fluxes warm the air mass from below. So there we also don't have so large temperature differences. And in the bottom panel, we have again the mean and the MCO anomalies, but now plotted as CARRA minus ERA5. We can see that CARRA is mostly a little bit warmer in the free atmosphere, but ERA5 is clearly warmer over sea ice. So you see here from 80 to 82 degrees north approximately. And like we've already heard before today, ERA5 is overestimating the sea ice temperature. It doesn't have the snow. So it's a good sign then that that CARRA is colder over sea ice than ERA5. If we also take a look at the cross-section from west to east, we get to see how it looks over landmass, over Svalbard specifically. And here we can see that ERA5 is actually warmer and more humid than CARRA. And like we also heard before, ERA5 actually underestimates the temperature on Svalbard. So again, this could be a very good sign for CARRA then. But to really know, you would need to compare to observations, of course. So this is not a very extensive comparison, but I extracted a small same-sized box region for both CARRA and ERA5 around Ny-Ålesund on the west coast of Svalbard, where radiosondes are launched, and I compared both for analysis to these radiosondes. So for a small region in the Arctic, and I should also say these radiosondes are probably simulated, so it's also not an independent comparison, but just to see how they both compare, here is CARRA minus the radiosonde temperature in blue, and ERA5 minus the radiosonde temperature in red dashed line. So we can see that the difference is actually a little bit smaller for CARRA. They are both colder than the radiosondes, but ERA5 a little bit more so than CARRA. So to briefly conclude, we found that the sensible heat flux is substantially higher in CARRA than ERA5, which could be partly related to higher wind speed and MCO index in CARRA, and a stronger response of the sensible heat flux to both predictors. And the latent heat flux, in contrast, is lower in CARRA, which may mean that it's then improved. We also found that during marine cold air outbreaks, these cold and dry anomalies or negative specific humidity anomalies are present not just near the surface, but throughout the entire troposphere in both reanalysis. We actually have a manuscript preprint available if someone wants to know anything else about the work, and I'm also happy to take questions. Thank you.